Greetings once again. So the last video you looked at, we talked about this idea of a force per unit charge, an electric field. This video is going to expand on that idea. So this is the formal definition for an electric field. Electric field is equal to the force per unit charge available at a particular point in space. It's a vector quantity. It's a ratio. It's got the units of newtons per coulomb. And if you were given an electric field function evaluated at a particular point, and you had a charge and you placed that charge at that point, and you wanted to know how large a force that charge would experience as a consequence of the field, you could take this relationship and manipulate it to come up with this relationship and determine that force. Which brings us to our example. So we've got a point in space. There's our little point. There's nothing there. It's just a point in space. You are told that at that point, the electric field is equal to 7 newtons per coulomb in the minus j direction. And in fact, you could actually take that information and present it in much the same way that we would present force quantities. You could identify the direction with an arrow, and you could identify the magnitude thusly. And having done all of that, a question you might run into is, how large a force will a minus 2 coulomb charge feel if placed at that point? So to begin with, the direction of an electric field at a particular point is defined as the direction a positive charge would accelerate if placed in the field at the point of interest. So looking over here, if this was the direction of the electric field, what it's telling you is that if you put a positive charge right there and let it go, it would accelerate in that direction. Put a little differently, if the charge that was generating the field was up here, and it was, say, positive charge, and you wanted to know what the electric field was at this point as a consequence of all this positive charge up here, the question you would ask yourself is, if I were to go ahead and put a positive test charge at that point right there, in what direction would it accelerate? Well, if there was a whole bunch of positive charge up here, it would repulse your positive test charge. It would motivate that positive test charge to move in this direction. That would be the direction of the electric field. That's actually the way you determine the direction of an electric field if you're not told in the problem what that direction is. In our particular problem, we were told the direction of the electric field. It's in the minus j direction. But that won't always be the case. In some cases, you will have to actually figure out the direction on your own. But that will come with time. In any case, the problem we're dealing with has an electric field that is down, and we've put a negative charge at the point of interest. So if positive charges are going to accelerate with the electric field, negative charges are going to accelerate in the opposite direction. And the question arises, how can we mess with the math in such a way that we end up with a force expression that's going to give us a force that's going to be in the plus j direction? Which brings us back to our force relationship. What's tricky about that force relationship is if we allow the sign of the charge to ride along in that QE expression, it will end up interacting with the sign of the electric field vector, and it will give us the correct sign for the force. Okay, this is technically not a kosher thing to do. The sign of the charge is telling you whether you have a preponderance of electrons or a dearth of electrons. It has nothing to do with direction per se. But we need some way of determining whether or not we're getting a charge moving in one direction or the other, because positive charges will go in one direction and negative will go in the other. And it turns out that if we allow that negative sign to ride along, it will do the job for us. So here is the calculation. We have F equals QE. Q is equal to minus 2 coulombs, where we're allowing the sign to ride along. The electric field is 7 newtons per coulomb in the minus j direction. The minus goes positive. We end up with a magnitude in the plus j direction. and that's the appropriate direction for the direction that we know that the electron's force is going to be in. So by allowing this sign to ride, we've ended up with the correct direction for the force. Bottom line, when using this relationship, you want to include the unit vectors for direction, and you want to include the sign that is associated with the charge. And that's the truth.